Well, look, it's a pleasure to be here. The topic is self-explanatory. We're going to nerd out a little bit on NLP, and then I'm going to tell you a little bit about the implications that we really face in bigger enterprise, specifically when it kind of interacts with the software piece and actually, actual productionization. So a lot of the work in NLP is focused on, as you have seen, research, better models, enabling, high performance models, and doing various tasks, so multitasking, so on and so forth. There hasn't, when you go out there, there isn't a ton of talks on, okay, how to integrate it for specific enterprise needs, right? So usually, it is becoming commoditized to a certain extent, usually to certain companies, and with very certain, patterns to be used. Okay, so this is kind of to help us, break that pattern and use it the way you want in your own organization, right? In various ways. So, just gonna get into it quickly. So obviously I'm from RBC, and we do a lot of cool stuff there, including NLP, computer vision, all the ones that was mentioned earlier. So all right, so let's see. Is this still truthful? So we're going to talk a little bit about low-level text processing so that you appreciate for all these data miners at every organization, and then we're going to take a quick look at the evolution of NLP. How is it that we got here? Really, we're dealing with really big models these days, and you see the parameter size in later towards the end of the slides. And then it has a ton of implications. Like you can't really embed these models in a web browser, right? So a ton of implications as to how you use it, right? So we go through the evolution. I have to talk about the surges of NLP. Those who have taken my classes are familiar with those, and some of those materials are also available on Agate Intellect's website. There are also YouTube videos that I'm not going to go too much deep because it's like 100 slides and I won't have the time. But if you want to review them carefully, go to Agate Intellect's website. I think the address is ai.science, and you'll have a lot of the theoretical NLP stuff there if you want to review them or look at them in detail. Anyhow, so surges of NLP we talk about, and then what does it all mean for R&D and products and right now, right? And that's something that we get to towards the end, and I hope for that to be a little bit of discussion. So I will start us off with the things that I believe matter the most, especially if you work in a bigger organization, right? Or any teams that wants to build a variety of products, not just one single product, right? And being able to iteratively update your application, right? Which I assume most of you or all of you would like to. Okay, so let's talk about, so I've lost count. There has been quite a few surges. I think I can still say that you got two big surges really of NLP. We're still in the attention surge, but let me categorize this a little bit better. So top left, you see your rule-based NLP, the good old applications. There was it goes back all the way to philosophy, empiricists and versus rationalism, right? So it is well rooted. I'm not going to go thousands of years back, but let's go 50 years back. There was a fight between these two paradigms, and at first the rule-based methods, survived partially. Thanks or no thanks to Noam Chomsky. He really bashed down the statistical method. We didn't have really, mathematically it made sense to a lot of us, but I think Skinner was, or one of the really renowned psychologists back in the day wrote a book. I think it was called actually Language, and a lot of the theories got really bashed down by Noam Chomsky. Anyhow, so people theoretically didn't buy it in. There was not a lot of performance, to showcase either, right? So rule-based NLP really, they thought they're going to solve AI in so we're talking about 50s or 60s in 5 years, and it didn't happen. Surprise, surprise, because the learning wasn't really there. And you want to move the system, you have to have another, the expert come in and please edit it, and it has to be super smart so that it can do a lot of things. And they're not, right? So we get to a slide that I showcase why it's such a challenging problem, and all of AI, not just NLP. Anyhow, so that's rule-based NLP. Then we get to the first deep NLP search. So this is a classical deep NLP. The architecture, let me see if the architecture in the middle is Yoshua Bengio's. We may actually go through it. So I'm going to talk about it. I'm not going to spend too much time right now. So there's, how it all came to be. I skipped the statistical NLP. Like that came about around, I think late 80s and 90s, and then as machine learning was taken off, all of that really took off. A lot of the classical models, those hidden Markov models, for those of you who go back that far, were really prominent in combination with Viterbi, and I think I'll have him in the talk. And you'll have, those CRF coming lately, I think 2010, 12. And moving on. So anyhow, I talked about the deep search, and suddenly a deep search happened, deep learning happened, and it was showing performance really well. Theory still has to catch up, right? I'm not claiming, but a ton of really good work in theory as well. And now, second deep search second NLP search is the deep, the attention search that I call, you see all the bears, and you see why it matters, right? So I'm going to go through, I'm an NLP person, there's no way I'm going to talk about MLS without NLP, but I think I'll show you why we got to appreciate, why, and it's going to only grow from this point on, the size of these models, which have huge implications for model ops. All right, so let's get to it. I'm going to be super. I'm going to be super quick on these slides. There's a ton of slides on, the dirt work of NLP. There are so many tools you can use to do low-level text processing, right? And you probably have heard of Spacey. NLTK is one of them. I'm not going to showcase all of them, but there are quite a few things you can do. So one of the things you can, obviously you need to have that, import the library. That's just it. And they have, these text collection objects, and a lot of them work in different ways, but similar purposes. They have a lot of objects that can help you, a lot of libraries that can help you out of the box. So anyhow, there's a collection object here in NLTK that you can easily use, and puts your, formats the text properly, tokenized. You can do a lot of stats on it kind of out of the box, but this is all low level, right? So no understanding here. So we're in the first, the classical NLP era, right? So there's a little bit of statistics, combination rule based, but there isn't really not a lot of language understanding in there. So we just bringing in those. Can you actually read any of these? You don't have to read the detail, but let me know if there is an issue. Just raise your hand. But anyhow, that's just importing a couple of books. Then you can do these things and getting word similarity based on the context, right? There is no vectors here, so this is very classical NLP, right? So no vectors right now, really. We just look at the context words surrounding similar words, and okay, this is these context is shared between the two words, therefore there are similar words, right? So a lot of templates were created back in the day in the rule-based era, and you can do basic lexical stats, as you can see on the screen. Okay, so you can get some score. The question is interesting. Compute what percentage of document a word constitutes, right? Very simple. And we get to the point that, okay, why should I care? How can I? Well, first of all, a lot of NLP applications actually use these in the past. One of the things that you can do, you can plot lexical dispersion, through time, how your, words are being used, so on and so forth. And it's informative. It is a method of feature extraction these days, but not beyond that. But back in the day was the NLP. All right, so you can have your lexical diversity. Publishers use that a lot to know if a textbook is rich or not. I won't go into too much detail, but one of the methods is type token ratio. Very, very simple mathematics. All right, so now let's talk about, and there's still more, but let me talk about how classically natural language was divided. How many of people in the room are actually familiar with linguistics or the layers of language? Okay, that's amazing. We study some of them in NLP. I suspect if you take an NLP course, some of it is discussed. But basically, languages are, they take in some audio signal, so some continuous signal. They process it. We know, it's been shown various times that humans can break them down into, these things called phonemes, so some mental representations of these sounds, and then all the way to morphemes, so like how these phonemes work together to mean something, actually. And they're variant across each level. They variant across languages, right? And then from morphemes, you go to, to words and, kind of the lexemes, and then from there, you go to sentences. But sentences don't really mean always the same thing. I can say, I don't know, it's kind of warm in here, but I'm indicating, I'm asking someone to, turn down the AC or open the window. So they can mean a lot of things. So there's this other layer called pragmatics. Anyhow, so it's super complex, right? That's all I'm trying to say. And then there are two different directions. You receive this information, you also process information, you output the same information, which is meaningful and relevant for your audience, okay? So anyhow, so I went through all of this. So meaning was semantics, and then what you actually intend to do with that meaning is pragmatic. So you could answer some of these questions now so far with NLP. How many times does the word LOL occurs in a text? Okay, so I've spent quite a bit of time, I realize. So let me, so there is a ton more you can do, but I really want to focus on the surges and how we get to the harder problems of LLMs. A lot of these algorithms are relatively simple, even through the classical. So I'm going to skip some of this. Even with the classical, NLP, even the classical machine learning NLP, the question was, how much is the algorithm going to take? The parameter size was like hundreds, so it wasn't a big deal. You could easily run it on a CPU. What really mattered was, optimization for algorithmic optimization. How do I optimize it? Which optimization algorithm I use? Which search algorithm I use? For the search space. So, and we could do it, very well, like beam search, and we get to those in a second. The text from the web is noisy. We can clean them up. Just gonna walk through the slides very quickly so that we get to the important stuff. We can process RSS, extract content of the post and clean it up, and do some local file operations, right, for text specifically. Okay, let's see. Yeah, so there's some links there. If the slides are shared, you can take a look if you want to process, PDF files, so on and so forth. Okay, so one example is very practical is chart distribution. So again, we're very low level, still very low level NLP. And with chart distributions, you can actually detect languages, right? So that's one of the use cases. You can treat them as features. Okay, and there's some considerations about what programming language you're using and what encoding it's using. So Python native uses Unicode, and with encodings it usually uses UTF-8, right? Just make sure you you do the right, you're dealing with the right encoding so that you can operate. Okay, so that's low level. Okay, good. So we got to the first surge of deep learning. And this is important. So this was talking about a little bit earlier about the complexity, and you were facing, a simple task, just opening the door using a doorknob, right? I've given, for those who've taken any of the classes of mine, I've given that example before. So if you want to, you have certain rules. You want, you have an actuator and some sort of a robot, you want them to open the door, and it sounds very trivial, right? But which way you twist the doorknob, how much force you use, what's the height of it? What are the dimensions of the doorknob itself? And if you want to just put down rules, it's just impossible, right? I think I've made that point, so I'm not going to get too much in depth. It's just impossible. So that's why classical, rule-based NLP really didn't succeed. All right, so let's get to the first surge. So neural nets, backprop happened. Now neural nets were actually a thing. You could use them. They were slow, but you could train them, and they showed some prominent, some prominent applications. But they were super slow. So they were really they tried to use some substitutes all the time. So it wasn't a lot of buy-in. And here's why they made sense, though. So let's say you have two words, three words, dog, rat, and mat, right? You go from layers of understanding, as I mentioned earlier on, from one layer of understanding to the next layer. It may, the meaning of, they may not really correlate anymore. So let's say mat and rat really correlate. Like they are really the same, from the phonology perspective, they're really the same, very similar, just one substitution between the words, between the letters, so M and R, right? I'm using letters because they're simpler to understand. But anyhow, but you go to dog, really no relationship between the two, but you can see rat and dog, although not really relevant regarding the letters or the phonemes being used, but semantically are so relevant. So why I'm saying this, because from one layer of understanding to the next layer of analysis, there could be a huge shift of relevance, right? And this is only, you can only capture this if you can process nonlinearities in general. Okay, so that's why really deep learning mattered. They could outperform a lot of the architecture. So I'm not gonna delve too deep. I think 45 minutes, much less time than I suspected it would be. Anyhow, so this is the first architecture that really gave rise to now deep language models. So before this, remember, there were HMMs, there were CRFs, conditional random fields, and you could predict the next word in the sequence. That's what all a language model was, right? And technically, that's how it is, and until some synergic magic happened. So this is from Yoshua Bengio Udem. Basically, it takes in a few words, some shallow representation, and predicts the next word. The issue is there is no really inherent time series into encoded in the network, right? And then therefore you have RNNs. And let's see, how many of you are familiar with RNNs? I suppose most of you are. Okay, wonderful. So I'll just go very quickly. So can someone tell me what the issue with RNN is? Exactly, long distance dependency, and what else? For those of you unfortunate to have trained them, exactly, it's vanishing exploding gradients. You see all these nans, and so they don't really attenuate. They don't really process information the way you want to. So long distance dependency and vanishing exploding gradients. So to tackle that, we have attention, right? So we have LSTM. I wish really I could go, but refer to the videos. I'm not going to go too much in depth here. Basically, you guys, these gates. If a signal is really weakening or dying, you amplify it. If it's too strong, you attenuate it so that you can keep your boat float. Okay, so but let's take a quick look at the same time there was this this other area that taking place with the autoencoder, regarding transfer language, a little bit an adaptation. So they did cool things at the beginning with them, but not really to the extent that we do here. So all autoencoders did was just encode and then decode, right? I suspect most of you are very familiar with this. You see why I mentioned this. It's super important for the latest surge. So the important is that you can now do machine translation end to end. Previously, I'm not going to go into how much of a suffer it was to build a machine translation system. Like too many components. Okay. Anyhow, so and then you get these shallow vectors. So we're I'll go very quickly, but basically you got your shallow vectors. So the point here is that you can do a lot of vector math. Okay, that's amazing, and they'll come together. But obviously, shallow vectors don't do any linearity. Right, so we covered quite a bit, but let's focus mostly on the two biggest problems that are still out there, but we really tackled them well: long-distance dependency and vanishing exponent gradients. So attention got introduced. The issue with attention was that so basically you still had the issues with the original RNN, well, some of them, because you have to process them in sequence, okay? I'm not going to go into the depth of it, but you can see some visualization of attention. This is amazing. First time, we use machine translation because it makes sense, when you're decoding which words of the source language to pay attention to when you're generating the target language. Anyhow, moving on, and there are different types of attention. If you want to ask me about it, I'll go in depth. And then we got to the transformer networks. So the point here, I think the main point to take away from transformer network, really the main source of innovation was just parallelizing attention, which meant a ton, because I see in the complexity in a few seconds. Now we can process really massive text, and you're not, the longest path isn't going to slow you down. The length of your sequence isn't that much going to slow you down in practice, right? So they actually work faster in practice than RNNs, right? So that's amazing. That's all it was, and everything that you see these days, various GPTs, almost every company has their own language model. They all use this parallelization. I'm not going to go into the details again because of the time. So let's get to the fun stuff. So now you have a model. Okay, so I'm going to skip beam search and TopK, and if you want to ask, let me know. I'll talk about those. But this is the complexity I was talking about. So your the sequential operations is ON. Your maximum path length is ON, and this is massive. Anyhow, but also the compute is growing. So. All right, so let's look at how parameters change. So from hundreds of parameters, the first machine learning models that I've trained actually had just a few hundred parameters. If it was in thousands, I would be surprised. And then you got BERT that suddenly brings it up. I'm kind of jumping through the history, but you get the point. 110 millions. Then you got GPT-2, 1.5 billion. GPT-3, 175 billion. I suspect very easily we hit trillion parameters. So this is massive. How do I really deploy such an application, right? And then also the patterns of transfer learning entirely changed. So it was, you look at the autoencoder, your decoder and encoder architecture. You form some sort of representation, and then you could downstream apply it to another task. So that's a kind of decoupled pattern. Another one, you could just use the same network as I see on is it your left too? Yeah, on your left. You can see, you just use a model, fine tune it, freeze most of the layers, maybe unfreeze some of the ones at the top or at the end, and then do your downstream task. Why does it matter? Because you don't want to train these massive models over and over again, right? Okay, so that was all it was before recently, and now suddenly look at all the way to the right. You get your GPT-3. You do multiple things at the same time. You can do summarization. You can do question answering. You can do translation. You can do cybersecurity. You can do just a ton of things at the same time with just the same language model using that prompt design. So how many of you are familiar with prompt design? Okay, some of you are. So for those of you know, it's this new method of transfer learning. Because of so much text and so much parameters, the network just learns so much that the designers don't really, really nobody can say they know exactly what the model knows. It just knows too much, okay? And that's why some of them got killed, But really, the prompt design is, okay, now I have this model. Let me give it a few examples of what you should do. So, you can give it an example of, malicious attacks, and then say it's malicious, right? And then the model would run like 5 examples. So few-shot learning, if you're familiar with it, you can really use. Oh, this is research by Google, by the way. Basically, you can easily transfer learn from these big models. There. So that's amazing. You can easily, with really good accuracy. So really few-shot learning is a thing now, right? And even zero-shot to a lot of extents, right? But what if I want to make the model do a certain thing that I want it to do, very delicately, right? As opposed to just classification, right? You can do prompt tuning, right? So with prompt design, you see that everything is frozen, right? And if you want to fine tune, then you have to do a lot of training, right? What if I just want to, make the model do certain things in certain ways without doing the tuning, but just changing the input? So this is a new way of talking to the model. This is, the prompt tune pattern you see in the middle, right? Which is massive. The implications are massive. I'm not going to go too much in depth. I just wanted you to have an idea how complex these things are. So they're just not massive. They're also very, very complex. So now, for you at your organization, you want to deploy a model, you may actually have to use, for privacy concerns and a lot of other reasons, you may actually want to use federated learning. So let's say the system is getting more and more complex. So with federated learning, how many of you are familiar with federated learning? Okay, a few people. So it's a more private manner and very, very optimized manner of training machine learning models. You have a lot of text prediction apps on your phones that you use all the time. Those are usually, Apple and Google usually use federated learning to train them. So basically how it happens is that you have a local version of the model and only the weights get transferred to a central. You don't send all the data. So it's very important. But see, the design is becoming more and more monolithic as we're carrying on. And then you also maintain privacy. So you use methods of differential privacy. So you use all of that on a model. So you don't want to repeat all of that over and over again. And then obviously, a lot of restrictions on data access. You train the model once. You don't want to, especially in organizations such as ours, you don't want to train the model over and over again. You want to give access to data over and over again, right? So all these implications can just make it very, very hard for a monolithic design. So traditionally, what happens, you have some input. Sorry, the text is perhaps a little bit too small, but these are just two different models. On top, you have your message routing system. Messages, natural language messages, and at the bottom you have your email classification. They're related, but you can have machine translation tasks, a lot of other NLP tasks, right? Previously, and a lot of times even today, the designs have been monolithic. The data comes in, you train this, a big model, and then you deploy it, or fine-tune this big model, and then you deploy it, and it passes over the results to to its end user, right, or the consumer. But then you have to repeat the entire thing again. You have to provision all the servers once again, be it cloud or on-prem, and all the other implications that I mentioned, or considerations that I mentioned earlier on. But with your microservice design, you can have this. You can deploy you can really break it the heck down. Whatever system you're looking at, just break it down into using some of the things that we talked about into something that gives out your embeddings, right? So break it down in a transfer learning pattern. You can deploy only one language model, a very, very sizable language model, billions or trillions very soon parameters, but use them for multiple downstream tasks, not just one. Right. So then, and the second models, they're smaller microservices because you can easily train them. You don't need as many parameters anymore. Your GPT-3 already understands it very, very well. You can just downstream classify the information coming out of. So your models won't even see. So there's a lot of privacy advantages here. All of the privacy, federating mechanisms, differential privacy algorithms, everything is already being applied to that big model. So your downstream models aren't really exposed to any risk. So it really matters for big organizations such as ours. Okay, I want to leave time. I spoke 2x of my normal speed, but we got it done. I got 10 minutes, approximately 10 minutes for a question, but I really want to hear your thoughts on this.
So you went very quickly through the entire history of NLP in half an hour, so thank you for that. So the absolute cutting edge right now is these enormous language models. Like at NVIDIA, we've got 500 billion parameter models we're working with regularly. We're in a great position at NVIDIA. We can do that. GPUs are cheap for us to use. Can you offer advice or opinionated comments for those who are in academia or smaller shops who might feel like they're missing out on that?
Yeah, absolutely. And let's start with NVIDIA. NVIDIA has a couple of academic programs. If you're not familiar with it, I'm sure we can provide you a link that will help academics. So if you want really your local servers, they would provide you with such. There is Canada Compute, if I remember correctly, is a federal program in Canada. You can just use the compute all over Canada. It's cloud computing. Students get some budget they can utilize, and then you have all the cloud providers also provide promotional credits to academic institutions. So if you're professors, if you're in academia, professors don't already have access to it, you can just directly contact them and they provide credits. And it's funny you mentioned that. We submitted a paper a while ago and they were like, why didn't you do these other ablation studies? And our answer was just, well, we ran out of credit. So does that answer the question? Yeah, so there are plenty of opportunities. Really, the tech companies are making it super easy, and no excuse for not using the cutting-edge technology. So if your organization isn't doing that, talk to me. I can give you a couple of convincing arguments.
Great talk, thank you. So I have a question actually about architecture. So there's this movement of trying to basically understand architecture. I've seen good papers on ConvNet, for example, trying to explain why, trying to explain the architecture based on actually sort of laws of physics that you want to have sort of rotation invariance, you want to have translation invariance and so on. The NLP architecture do you have any thoughts on why the architecture is the way it is and sort of trying to come up with is there have you seen papers trying to explain it on linguistics theory, for example, of why these structures are the way they are?
Yeah. I have to think about it. That's a great question. I have to think about it, but I have some thoughts that I'll share. So one is that, as you well know, computer vision and deep computer vision and NLP have really stole from one another, for the lack of a better term, really. They really collaborate. Everything, CNNs, people in NLP were but they're not really order sensitive CNNs. They don't track, but they worked well on a ton of NLP applications, better than those that were order sensitive, including HMMs and CRFs. So there's a lot of collaboration, so we keep looking at what we do. Attention is the other one. I think attention came out of computer vision, and just somehow at some point it made sense to an NLP person for machine translation to use those ideas, with self-attention and local. The other one is, that I haven't used them for NLP, but I was surprised if they're not used already for NLP, are capsule networks. They really keep, try to, keep some, the structure of whatever input they have, right? And they're more generics. That's the other thought that I have. In NLP in general, you have, I went too quick, but you have two sources of structure. One is sequential, the other is hierarchical, right? And hierarchical was the one that I was talking about, when you go from this meaning of word, from the looking at the sound of word to the meaning of it, right? And that exists across NLP, across all the different layers that I named, right? So these have been, and there has been a lot of attempts in capturing and maintaining them. So every time there comes out a new model for NLP, all the way to attention, then suddenly this work gets published that can improve the performance by injecting this structure in it. So for attention, for example, with Lisa, I have a YouTube talk, you can go take a look. It's called Linguistically Informed. Look at the rest. I don't remember, semantic something. I don't remember what exactly it was. But basically what it does is it enforces via cost functions and input patterns, and enforces the neural net to capture some of the structure of natural language, right? Both sequential and hierarchical, so syntactically informed, I think, language model or something. Anyhow, so those are my thoughts.
Okay, thank you.
Yeah, you're welcome.
Hi. So I guess the question that I have is a bit more generic, but I'm not sure whether there would be even an answer to this. But you presented different techniques that could be used for NLP. Is there a rule of thumb when it comes to, depending on how the data is, what sort of model should be implemented? What sort of features or aspects of things are you looking at when you're basically selecting what model to be implemented for specific data sets?
Could you rephrase the question?
Yeah.
Thank you.
So how do you select what model to use? Plain and simple.
Okay, model selection. But what considerations specifically you're looking at? Given this
Yeah.
size
So I'm in AML, anti-money laundering. So banking perspective, data privacy is a very huge thing. And so when it comes to selecting different models or specific models, you have to basically account for those aspects even when you're implementing. In that specific case scenario, what would you suggest? What would be a good approach when you're basically looking into data privacy as a whole and implementing NLP in that aspect of things?
Okay, gotcha. All right, great question again. So basically, my very applied. So most of my work is in the industry. So there's a lot of experience that I don't get to really share with you. But when I look at any problem, including AML, you want to start with with the lower threshold of model complexity, because if it does really well, then it does really. It really depends on the complexity of the task. And there, if you use a lower parameter size, you're not really too worried about the privacy aspects. Bigger, mostly deep models do have the memorization problem because of the depth and the representation that exists and stays with them, right? So that's where I start. And then if you want to use deep algorithms, I would suggest, usually you do that because you want to improve the performance, right? And you have the compute and everything set up for it. Then you have to make sure the privacy is there. So you can use various techniques, including like if you have edge devices, fair learning. If you don't have edge devices, direct differential privacy, horizontal or vertical. And then I would say if you're doing, are you doing just one task or there are multiple? Just
multiple tasks, not
multiple tasks.
Yeah.
Okay. Then I would suggest just follow, what I just shared. So make sure you can safeguard your biggest chunk of the model that has memorization risk, including language model, and the rest you can, if you're using a linear classifier, there isn't really much of a risk there.
So, sorry, a follow-up question that I have. Because there's so much research that's being done consistently within NLP, what model, or is there a rule of thumb as to what you should be looking towards when implementing these new approaches into the work that you're doing?
Is there any what that you want?
So is there something that you should be looking, like parameters or some, because research is different from actually real life implementation of models, right?
Yeah.
Where do you draw the line between, yes, it could work, no, it couldn't work in the case scenario of real life?
Oh yeah, I mean you got to test it. Okay. So you see it on GitHub, you see it on a paper. No guarantee it's gonna work.
Yes.
And multiple times we did our best really, and even contacted the authors, right? And we couldn't reconstruct the results. So a lot of times it happens, and some method that has worked for somebody else very well may not work for you. So I'd say there is really not a shortcut.
Okay.
You have to experiment with them, but usually with a specific model, usually some prominent models get with all the ratings that are there, either on GitHub or some of the research tools that are there, models with code. By the way, I remember the paper's name was linguistically informed self-attention, right? If you want to look it up. Yeah. So that's use your resources and pick the top ones, but you have to experiment before using.
Okay, sounds
Yeah.
fair. Thank
Hopefully
you.
that helps. Yeah.
Excellent talk.
Yeah. Absolutely. Thanks very much. Thank you.